In this video, I'm going to introduce you to a couple of ways that we represent chemical structures in this class that you probably did not encounter in general chemistry. Let's start by considering this Lewis structure. In this class, we have to write a lot of structures, and it would get really tedious if we had to draw full Lewis structures all of the time. So we abbreviate the Lewis structure. And one way of doing this is to write what's called the condensed structure. So the Lewis structure is shown in purple, and we are going to abbreviate the boxed atoms here in pink as simply CH3. Then we're going to move to the right and abbreviate the next group as CH2. Again, the next group, CH2. The oxygen we're just going to put in there as is. And then we're going to treat the next group in yellow as CH2, and then finally another CH3 at the end. So we would say that the overall condensed formula for this Lewis structure is CH3, CH2, CH2, O, CH2, CH3. When we have a Lewis structure like this and we want to convert it into a condensed structure, we go along the carbon chain as we did before. And so this CH3 group that I'm circling in blue would match up with this CH3 group here. And then the CH2 that I'm putting in red corresponds to the CH2 group here. Let's use yellow to do this CH2 group here. And then we come across this red carbon, which has several groups on it. And so, for example, we have a hydrogen up here, which we will go ahead and write in next to the carbon. But then we have a group in two different directions, and so we have to indicate that this particular carbon has a couple of different groups on it, and you have to put one of them in parentheses. I'm going to choose to put this CH2, CH2, CH3 in parentheses, and so that is what is overwritten here. And then on the end, I'm going to go back now to this CH3 group, and that is what is on the end down there. When you have a group like this that you have to put in parentheses, this is called a branch. And so we say that the red carbon is branched because it has carbon groups going off in multiple directions. The condensed formula for this Lewis structure would appear as CH3, CH2, CH2Br, with the bromine atom written on the end. If the bromine were on the other end, like we see at the bottom, you would write this as Br, CH2, CH2, CH3. But hopefully you're able to tell that really these are the exact same structure. And so if you were to flip one of them around, you would have the other. What may not be quite as obvious is that all four of the structures on this slide are actually identical to one another, and they are also the same as the two structures on the previous slide. We could represent any of these structures with the same condensed structure shown here at the bottom. So hopefully you're able to tell that if we took, say, this structure here and simply flipped it, we would have the structure up at the top. Or if we took this structure here and flipped it around, we would have the structure at the top there. In terms of the positioning of the bromine atom, these are all sigma bonds here that are free to rotate. And so where the bromine is in space in this particular example does not matter. There are times when the placement of an atom would give a different condensed formula. So for example, on the previous slides when we were putting bromine on the end carbon, that's a different situation than putting the bromine on the middle carbon. These of course are constitutional isomers, which you should know from general chemistry. And the formulas would appear as follows. And so the one on the left would have the bromine in the middle, and of course the one on the right would have the bromine on the end. Another time we have to be careful about where we place atoms is when we don't have free rotation about a given bond. So for example, putting bromines on the opposite side of a double bond versus on the same side of a double bond is not the same, because unlike a sigma bond, you don't have free rotation about a pi bond, so you can't just interconvert from one to the other by rotating. So these are actually not the same because there is no free rotation. You will also encounter this situation when you have cyclic structures. So for example here, once again, having the bromines on opposite sides versus the bromines on the same side is not the same thing. Even though these are all sigma bonds, because it's cyclic, they cannot rotate around, and so they're kind of stuck that way. And so these are also not the same compound. I want to show you a few groups that tend to have a unique way of being represented, and one of those is here. It's called the aldehyde group. And notice that the carbon, oxygen, and hydrogen circled in pink are represented by a CHO notation. If you were to flip that the other way, which is actually just the same molecule flipped around, we would still represent this as CHO. And so when you see this notation, it's correlating to that structure right there, the aldehyde. Similarly, the carboxyl group is often abbreviated COOH. So we call this group here the carboxyl group, and it will be abbreviated COOH. Once again, if you were to flip that around, it would still be COOH representation. Multiple bonds are sometimes written into the condensed formula, but may not be. For example, the condensed structures in purple are both acceptable and equivalent ways of abbreviating the Lewis structure in green. If the multiple bond is not written into the condensed structure, you have to use the fact that the two carbons that I have boxed in red there appear to have an incomplete octet, and you have to infer that a double or triple bond must be present. In our example here, the two carbons boxed in red would not have complete octets without a double bond. Many organic molecules contain a carbon-oxygen double bond, otherwise known as a carbonyl group. And just like the carbon-carbon multiple bonds, the carbonyl group may or may not be written out in the condensed formula. So both of the condensed structures on the right are equal and acceptable ways of writing the Lewis structure on the left. Now we will look at yet another and probably the most commonly used way that we represent organic molecules and ions. We saw that when we went from a Lewis structure to a condensed structure that we were able to simplify groups of atoms into an abbreviated notation. We're now going to simplify the structure even further into what is called the skeletal structure. And so here in red is the skeletal structure that would go with the condensed and Lewis structures above. Let's look at a simple example. So as of right now, we know how to take the Lewis structure on the left to the condensed structure on the right. To get to the skeletal structure, we're going to draw in a zigzag line where the ends of the line and each bend in the line represents a carbon atom. So here is our skeletal structure where two of the carbons are being represented on the ends. So that would be the CH3 groups. And then the two carbons in the middle at the bends, so to speak, are the CH2 groups. Normally, the hydrogens are not drawn in on a skeletal structure, particularly on carbon atoms. And the implication is that unless you are told otherwise, you assume that there are enough hydrogens on each carbon to complete the octet of the carbon. Let's do another one. The skeletal structure for this molecule is seen in blue, and the colored arrows point to each carbon that is being represented. Notice that there is an oxygen or an OH group drawn in here on this carbon. And that's because if we didn't put the OH group there, we would assume that there were just hydrogens around that carbon, enough to complete its octet. So typically when a heteroatom, or an atom other than carbon or hydrogen, is present on a given carbon atom, then you need to draw the heteroatom in. The condensed structure for a cyclic compound is really not that condensed. You can see going from the Lewis structure in green to the condensed structure in purple that you still have to draw quite a bit. So the skeletal structure in yellow correlates to the 6 carbons there at each bend, and it's much simpler to draw. Multiple bonds are drawn into the skeletal structure, as seen in yellow with the double bond and in purple with the triple bond. If you do need to incorporate a triple bond into a skeletal structure, make sure that you draw it at 180 degrees, since we know that that is the bond angle for sp carbons. Don't get into the habit of drawing bent-looking triple bonds. Here's how we translate a few common groups into a skeletal structure. So the carboxyl group that we saw earlier would appear like this. Notice that the fluorine atom in this structure is also incorporated in. And then on the right we have the carbonyl group circled in orange, and it would appear in the skeletal structure pretty much the same way, with just a bend there for the carbon. And then you have the 2 chlorine atoms also incorporated into that skeletal structure. The more problems that you can do practicing interconverting between Lewis and skeletal and condensed structures, the easier it will get, I promise. You just need to get familiar with it, get used to seeing it, and after you work on this for a few days, it will be second nature.